Hey, so I'm Victoria Contreras. I'm in Lab M on Tuesdays from 3 to 6. My observation video was of a man walking at a constant rate, and then I also used a model in order to predict his final position. The result of both of these tactics was that because of the momentum principle, whenever you have F net equals zero, your forces equal 0, you're going to have a constant velocity. So this is the observation I made with the video. Here's the man walking. As you can see, I set the origin right behind him at the pole, and then I used this right here, 0.15 meters, in order to gauge the distance. I had him walking along the positive x-axis this way. I switched it around because that was the rate of what he was going. Then I used the middle of his body as his mass point to track as he was going along. So as you can see, the time frame has about 50th of a second between them. I started tracking him while he was walking, not when he started, and I stopped tracking him before he stopped. So it was in a constant velocity all throughout. The data I got from this video was of my initial velocity of 0.103 meters, then I had a final velocity of 1.327 meters. Of course, my initial time was 0 seconds. My final was about 1.6 seconds. In order to get my initial velocity, I took my change in position divided by my change in time and got 0.74 meters per second. And then from there, I used this information for my model right here. This is the code for the model. As you can see, our forces equal 0. So that we have our constant velocity. I was taking it over an interval of 2 seconds because my time was about 1.6. Right here is the equation used. So you have your final velocity is equal to your initial velocity plus your forces divided by mass times your change in time. But if your force is equal 0, then this over here is obviously not going to matter. So you know your V final equals V initial, aka constant velocity. So the visualization for that, as you can see up here, I plugged in my position and my initial velocity. Start time was 0, and my delta time for my visualization for my model is 0.01, so a very small time frame. So whenever we run this, you can see it starts a little bit above the origin like my actual model did, and goes at a constant velocity to the left along the positive x-axis. As you can see right here is a positive linear relationship. And then you can see over here, you compare the model and compare the actual observational data. They are of the same information, so they proved each other. But now the question is, what if I'd made a different choice of origin? Well, if I made a different choice of origin, see here, so if I had made these negative, so that everything was going along the negative x-axis, it would be the same graph, but what would happen is that we'd have a negative slope. So let's see here, because it'd be going, there we go, see? So there's our negative linear relationship. And our second question was, what does this mean? Well, it means that the pushes and pulls of our system come to a total of 0. So there's nothing affecting the velocity, so velocity isn't going to change. As I put down here, that in order for there to be a constant velocity, the net force has to be 0, which can also imply that in order for the velocity to change, there has to be a force. So there you go. That's the end of my video.